Welcome to Bedtime Astronomy. Explore the wonders of the cosmos with our soothing Bedtime Astronomy podcast. Each episode offers a gentle journey through the stars, planets, and beyond, perfect for unwinding after a long day. Let's travel through the mysteries of the universe as you drift off into a peaceful slumber under the night sky.
I want you to imagine an object that is just so unbelievably dense, possessing such an incomprehensible amount of mass that it weighs 1 billion times more than our own sun.
Which is, it's a scale that just totally defies human intuition.
Right. It breaks your brain a little bit.
Yeah.
But take that image, that unimaginable behemoth, and I want you to put a second one right next to it.
Oh, man.
Yeah. Picture these two galactic giants. And they're locked in this high-speed, inescapable binary orbit, just whipping around each other mere moments away from a cosmic collision that is literally going to warp the foundational architecture of the universe itself.
The kinetic energy and the gravitational forces involved at that scale, well, we are talking about the physical deformation of space-time here. It's being stretched and squeezed by two supermassive objects in their final in-spiral phase.
And as of April 2026, this whole scenario has moved entirely out of the realm of theoretical modeling. Like, we aren't just guessing anymore.
No, not at all. We have the data.
Exactly. We are looking directly at the galaxy Markarian 501, or Merc 501, which is positioned in the constellation Hercules.
Right, about 456 million light years away.
And researchers have uncovered the very first direct, unambiguous evidence of a close pair of supermassive black holes on the absolute brink of merging.
Which is huge, because catching a binary system in this specific final act, it's been this decades-long pursuit in astrophysics.
We're going to completely unpack this today. We're going to map out the life cycle of these central galactic objects, look really closely at the 23-year-long radio astronomy stakeout that cracked this specific system open.
A literal stakeout, just staring at this galaxy for over 2 decades.
Yeah, and we'll break down how the impending collision of Merkle 501 is forcing this massive pivot in how we actually do astronomy. Because when telescopes hit a hard physical wall, tracking a merger like this means we have to measure the gravity itself.
Exactly. We basically have to transition from electromagnetic observation to gravitational wave tracking. It's the only way forward when they get this close.
So before we get into the crazy mechanics of the collision in Markarian 501, we really have to look at why this merger has to happen in the first place. The weight problem.
Right, the accretion problem. It's one of the sharpest constraints we have in black hole astrophysics.
Because if you look at the mass of these objects, hundreds of millions, sometimes billions of solar masses, the standard models of how they eat or accrete matter, they just fail to explain how they got so big within the 13.8 billion year timeline of the universe.
Yeah, we know that supermassive black holes reside at the center of virtually every large galaxy. We have a Sagittarius A star right in the middle of our own Milky Way.
But they can't just grow infinitely fast, right? Like, as matter spirals inward, it forms that accretion disk.
Yeah, and viscous friction heats that material up to extreme temperatures. It emits intense radiation.
And that radiation actually exerts outward pressure, doesn't it?
Precisely. It pushes back.
The Eddington limit.
Yes, the Eddington limit. It's this physical threshold where the outward radiation pressure of that glowing disk perfectly balances the inward gravitational pull of the black hole.
So it's essentially a speed limit for eating.
That's a great way to put it. If the mass flowing in exceeds that Eddington limit, the radiation pressure just blows all the surrounding gas and dust away.
Wow.
Yeah, it completely cuts off the black hole's fuel supply. So it's an inherent self-regulating mechanism. It strictly limits how fast a black hole can grow just by pulling in gas.
So if you calculate the maximum theoretical growth rate from a tiny stellar mass seed black hole up to 1 billion solar masses, keeping that speed limit in mind,
the universe simply isn't old enough. It's just not.
It's like trying to explain how someone ate an entire elephant and realizing they couldn't possibly do it one bite at a time. They must have just absorbed another giant eater.
Exactly. The math absolutely requires a shortcut. You don't build a 1 billion solar mass black hole by pulling in interstellar gas slowly over time.
You build it by smashing two 500 million solar mass black holes together.
Right, hierarchical merging, which integrates perfectly with our models of how the universe's structure formed. Galaxies collide and merge all the time.
And when they do, their central supermassive black holes are dragged along for the ride.
Yeah, they're subjected to something called dynamical friction. They interact gravitationally with the surrounding sea of stars and gas in the new, bigger galaxy.
They sort of bounce around and lose energy.
Basically, they transfer some of their orbital kinetic energy to the stars, flinging those stars outward, which means the black holes themselves lose energy, they sink toward the center, and eventually form a binary pair.
Okay, but if galaxy collisions are so commonplace, why has this final close pair phase completely eluded our detection until right now? What makes this final phase so impossible to see?
Well, the theory hits a massive bottleneck right there. It's why finding the Merc 501 binary is such a breakthrough.
Right.
Dynamical friction works incredibly well at large distances. It brings the black holes from the outskirts down to the core. But once they get within about 1 parsec of each other...
Which is roughly, what, 3.2 light years?
Yeah, about that. Once they hit that 1 parsec distance, the mechanism just breaks down entirely. It's called the final parsec problem.
The loss cone depletion, right?
Exactly. By the time they're that close, they've acted like a massive gravitational slingshot. They've ejected almost all the stars in their immediate vicinity.
So the loss cone, the area where stars could intersect their orbit, it just empties out.
It becomes completely barren, and without any more stars to interact with, the dynamical friction just stops.
So the orbital decay stalls out. They're stuck.
They're completely stuck. Theoretically, they could just orbit each other indefinitely, separated by a single parsec, totally unable to close that final gap because there is nothing left to bleed off their momentum.
Wow. So to overcome that final parsec, you need something extreme.
Right. Either a massive influx of new gas to provide viscous drag like a wet merger, or a third supermassive black hole crashing the party from a subsequent galactic collision.
Just to destabilize things enough to get them closer.
Yes. Because only when they cross that final parsec threshold can they get close enough for gravitational wave emission to take over. That becomes the new primary way they lose energy.
Which really brings into focus why detecting this system, MEC 501, is just so profound. We aren't just looking at a binary system. We are looking at a system that has actually successfully navigated that final parsec problem.
Exactly. It's past the bottleneck. It is deep into the gravitational wave emission regime.
But seeing that requires cutting through the densest, most chaotic regions of space. I mean, galactic cores are totally obscured by incredibly thick toruses of dust and gas. You can't just use a normal optical telescope.
No, optical wavelengths are entirely useless there. It's just a wall of dust. That is where very long baseline interferometry, or VLBI, becomes essential.
Right. And this is where the team led by Silke Britson at the Max Planck Institute for Radio Astronomy comes in. They bypass the optical problem entirely by relying on high-frequency radio observations.
Yeah, because radio waves can penetrate that circumnuclear dust porous without scattering too much. It lets us actually resolve the immediate environment of the black hole itself.
And they specifically focused on the relativistic jets. MEC 501 is classified as a blazar, right?
Yes, which means its primary jet is oriented at an extremely narrow angle relative to our line of sight. It's basically pointing right at us.
Like staring down the barrel of a cosmic flashlight.
Exactly. And the relativistic beaming, or Doppler boosting, makes the jet appear exceptionally bright because the plasma is moving toward us at a huge fraction of the speed of light.
Okay, so tell me about the actual mechanics of these jets.
Well, the Blandford-Znajek process driving those jets is critical here. The supermassive black hole is rotating, right? And that rotation actually twists the space-time around it.
In the ergosphere.
Right. And that twisting winds up the magnetic field lines threading through the accretion disk. It creates this immense magnetic tension.
Which just violently accelerates plasma outward along the rotational axis.
Boom, you get a jet. And for decades, the VLBI data from MEC 501 showed this really powerful, highly variable single jet structure, which is standard for a blazar.
But the Max Planck team didn't just look at a single snapshot. They utilized a 23-year archive of this VLBI data.
A 23-year stare. They weren't just looking for a high-resolution picture. They were looking for kinematic evolution over more than 2 decades.
It's like watching a time-lapse of a creeping glacier, only to suddenly realize decades later that there are actually 2 glaciers moving together.
That's a perfect analogy, because within that massive 23-year data set, they isolated the signature of a second, entirely distinct jet.
But wait, space is full of interference and radiation. VLBI data on blazars is notoriously messy. How do astronomers distinguish an entirely new second jet from just a burp, a flare, or some distortion in the primary jet we already knew about?
That's the million-dollar question. Because a knot of plasma moving down the primary jet or some instability in the flow can easily mimic a secondary structure.
So how do you prove it's a second black hole and not just a glitch in the single jet?
Rigorous kinematic proof. You have to look for sustained, non-radial motion. A plasma shock or a flare within a single jet will propagate outward, generally following the established flow of the jet.
Even if it expands or dissipates, it still moves down the same path.
Right. But what the team observed in MISRC 501 over those 23 years was a secondary structure that originated behind the primary core emission, and it exhibited a distinct, repeating counterclockwise motion around it.
Oh, wow. So it was orbiting.
The motion is the smoking gun. A localized instability does not establish a sustained orbital trajectory around the primary core.
So the only physical mechanism capable of generating a secondary, tightly beamed outflow that is actively orbiting
Is a second supermassive black hole, one that is actively accreting matter and powering its own independent jet.
That is just mind-blowing. And the realization that this second jet was moving like that, it opens up this wild new reality about the whole system. The entire galactic core of Markarian 501 is in a state of chaotic motion. Yeah, the presence of the second jet also provides the framework for understanding the larger anomalies in the system. The entire primary jet structure exhibits this pronounced swaying motion.
Silke Britson compared evaluating the data to being on a moving ship. The entire system is precessing.
Yes. The orbital plane of the binary is essentially wobbling.
Because if you have two supermassive bodies in a tight orbit, their individual spins and their orbital angular momentum are constantly interacting.
Frame dragging. The lens-thirring effect becomes incredibly pronounced at these masses in proximity. The rotating masses literally drag the local fabric of spacetime along with them,
Twisting the orientation of the accretion disks and the jets they produce.
Exactly. So the angle of those jets relative to Earth is in a state of continuous, predictable change. The sweeping motion alters the beaming effects we observe.
And this wobbling, this precessing geometry, is what ultimately led to that massive event in June of 2022, the Einstein ring.
Yes. Gravitational lensing in action. Break that down for me, because the physics of gravitational lensing are just wild. It happens when a massive foreground object warps the spacetime around it, bending the path of light from a background source, right?
Right. But the specific alignment required to produce a complete ring, rather than just an arc or multiple blurry images, requires an almost mathematically perfect syzygy.
A perfect alignment between the observer us, the lens, and the source.
Precisely. It relies on the impact parameter and the specific orientation. So in June 2022, the precession of the binary system brought the primary, more massive black hole directly across our line of sight to the base of the secondary jet.
Wow. So the primary black hole acted as the gravitational lens for the second black hole's jet.
Yes. Because the alignment was so precise, the radio emissions from the secondary jet passing through the primary's gravitational well were deflected equally in all directions.
It's like looking at a candle flame through the thick base of a wine glass. The glass bends the light into a complete circle. But here, the wine glass is a supermassive black hole.
That's exactly what it looks like. The warped spacetime stretched that emission into a perfect, closed, circular contour around the primary black hole's position, a tangential caustic.
But let me ask you this. Does this kind of perfect ring-forming alignment happen on a regular schedule due to the orbit? Or was June 2022 just a moment of incredibly lucky cosmic timing for us?
Well, because of the precession, it is a transient alignment, so catching it in a 23-year window is an incredibly rare observational triumph. It's a huge stroke of luck, but it's also a testament to just continuously watching the system.
And catching that ring wasn't just for a cool picture, right? It provided direct geometric confirmation of the mass distribution and the separation of the two black holes.
Exactly. The radius of the Einstein ring, the Einstein radius, is directly proportional to the square root of the mass of the lensing object.
So by measuring the angular size of the ring and combining it with the data from the 23-year VLBI study, they could finally lock down the orbital parameters of the binary.
With unprecedented precision, and the numbers they derived are just staggering.
Let's get into those numbers, the final countdown. Because the orbital period they calculated is just 121 days.
Which is incredibly fast. And the physical separation between the two supermassive black holes is calculated to be between 250 and 540 astronomical units.
Wait, 250 to 540 AU? I mean, that sounds like a big number, but for objects weighing hundreds of millions or billions of solar masses, that is terrifyingly close.
It places them deep into the strongly relativistic regime. I mean, the actual physical size of the black holes. Their Schwarzschild radii occupy a significant fraction of that space.
For scale, 250 AU is roughly 6 times the distance from our sun to Pluto.
Yeah, that's practically touching in galactic terms.
And 121 days is basically a semester of college. And these billion sun mass objects are completing a full lap in that time. The gravitational forces at play are unimaginable.
For objects of this mass to complete an entire orbital circuit in just 4 months, they have to be moving at a significant fraction of the speed of light.
The sheer kinetic energy driving that 121-day orbit dictates an incredibly aggressive rate of orbital decay, doesn't it?
It does. The system is governed by Peter's equations for gravitational radiation now. It's shedding massive amounts of orbital energy and angular momentum by radiating low-frequency gravitational waves.
And the decay rate accelerates exponentially as they draw closer.
Right. The power radiated by gravitational waves is inversely proportional to the fifth power of the orbital separation. So the closer they get, the faster they fall in.
Which brings us to the timeline.
Yeah.
Because the calculations place the final coalescence of these two behemoths within approximately 100 years.
Just 100 years. We are not looking at a merger on some vague cosmological timescale. We are looking at an event that will occur within a human generational time frame.
Cosmic microsecond.
Exactly. And the steepness of that in-spiral curve over the next century is going to be profound. The orbit will continue to shrink. The period will drop from 121 days down to weeks, then days.
Until the event horizons finally intersect and just ring down into a single newly formed black hole.
Yeah.
Okay, so if they are that close and moving that fast and going to merge 100 years, why can't we just point to the biggest telescope we have at Hercules and watch them crash?
And that is the ultimate frustration of observational astrophysics right there. The system is 456 million light years away.
Right.
At that distance, an orbital separation of 250 to 540 AU translates to an angular resolution requirement on the order of micro-arcseconds.
Which is too small.
Way too small. Even the Event Horizon Telescope, which famously imaged black holes in 2019 and 2022, it operates in the tens of micro-arcseconds.
So it's just a hard physical wall.
The physical Rayleigh criterion prevents us from ever optically or radiometrically resolving the two distinct event horizons right before impact.
So the actual physical merger will remain visually unresolved. A single point of intense radio and X-ray emission is all our telescopes are ever going to capture.
Yeah. But that inability to see them as two separate objects is precisely why Merc 501 is fundamentally shifting our observational paradigm. We are moving toward continuous gravitational wave astronomy.
Invisible ripples. We essentially have to trade our eyes for our ears.
That's exactly what we have to do.
Because we won't be able to see the splash of the collision, but we will absolutely feel the ripples hitting the shore.
Right. We have to move past the electromagnetic spectrum entirely. Now, LIGO and Virgo have revolutionized astrophysics by detecting high-frequency gravitational waves from stellar mass black holes.
But a supermassive binary on a 121-day orbit operates at a vastly different frequency, right?
A completely different scale. The wave frequency is basically twice the orbital frequency. So for a 121-day orbit, we're dealing with gravitational waves in the nanohertz regime.
Meaning the physical wavelengths of these gravity ripples span light years.
Yes. Ground-based interferometers like LIGO are entirely blind to these frequencies. To detect nanohertz gravitational waves, you need a detector baseline on a galactic scale.
Which sounds like science fiction, but we actually have one. Pulsar timing arrays.
The European Pulsar Timing Array, Nanograv, and the Parkes Array.
Explain how a pulsar timing array actually works as a detector. How do scientists use the steady ticking of dead stars to feel gravity warping?
It's brilliant, really. The methodology relies on millisecond pulsars. These are ultra-dense neutron stars that have been spun up by accreting material from a companion star.
So they spin incredibly fast.
Rotational periods on the order of milliseconds. And because they have this immense moment of inertia, their rotation is incredibly stable. They function as highly precise celestial clocks.
And we can model their radio pulses down to the nanosecond.
Exactly. We account for incredibly complex variables, including the interstellar medium and the proper motion of the pulsars themselves. We know exactly when a pulse should hit our telescopes on Earth.
So what happens when a nanohertz gravitational wave rolls through?
It propagates through the local space-time between Earth and that monitored millisecond pulsar. It physically perturbs the space-time metric. It alters the geodesic path the radio pulse has to travel.
It stretches and squeezes space itself.
Yes. The wave induces a quadrupolar distortion in space-time. As the space between Earth and the pulsar is stretched, the radio pulse takes a slightly longer proper time to arrive.
So it arrives slightly late, a positive timing residual.
Right. And as the space is compressed, the pulse path shortens. It creates a negative timing residual. It arrives early.
Wow. So by monitoring dozens of these millisecond pulsars distributed all across the sky, astronomers look for a very specific pattern in these early and late arrivals.
The Hellingsdown spatial correlation. It's a specific geometric signature in those timing residuals that can only be produced by a passing gravitational wave.
And in 2023, these array collaborations actually found evidence of a gravitational wave background, right?
Yeah.
Like a universal hum caused by supermassive binaries everywhere.
They did, but up until now, they've only been focused on that stochastic background, that general hum. MEC 501 changes that focus entirely.
Because MEC 501 is the perfect candidate to link specific waves to a specific binary.
Exactly. Because the orbital parameters are now known. We know the 121-day period, and we have the 100-year countdown. We know exactly what frequency to look for and how that frequency is going to evolve.
Because as the orbit shrinks, the velocity increases, and the frequency of the emitted gravitational waves shifts upward.
Right. The chirp mass of the system dictates the rate of this frequency evolution. And over the next few decades, MEC 501 will move dynamically right through the sensitivity band of our pulsar timing arrays.
So as co-author Hector Olivares noted, we might soon see the frequency of these timing residuals steadily rise. We are getting a front-row seat to the merger.
It provides a real-time, continuous track of the final in-spiral. The gravitational wave data will let us measure the mass ratio, the spin alignments, and the orbital eccentricity with a precision that optical telescopes could just never achieve at 456 million light-years.
It really is a masterclass in modern astrophysics, just the entire progression of this discovery.
It really is.
I mean, you start with the theoretical imperative, the idea that supermassive black holes must grow through hierarchical merging to overcome the final parsec problem.
Right. The math said it had to be happening.
Which leads to the grueling 23-year VLBI campaign just staring at the radio frequencies until they isolate the kinematic signature of a precessing secondary jet in Markarian 501.
And then the precession of that system yields the June 2022 Einstein ring, that lucky moment of perfect gravitational lensing that locked in the orbital parameters.
Revealing a 121-day orbit, a separation measured in mere hundreds of astronomical units, and a 100-year countdown to an impact that will generate a massive spike in nanohertz gravitational waves.
It's all connected. The tracking of those waves via the shifting paths of millisecond pulsars, it represents the absolute cutting edge of multi-messenger astronomy.
From identifying a system through the relativistic beaming of its plasma jets to calculating its ultimate demise through the measurement of space-time strain, it's an incredible evolution of our capabilities.
It really shows how astronomical progress relies on shifting our perspective. When looking at light is no longer enough, human ingenuity figures out how to measure the ripples of gravity itself.
I want to leave you, the listener, with one final kind of haunting realization to mull over. We've talked a lot about the 100-year countdown. But think about what the vast distance to Markarian 501 actually means in the context of this timeline.
Right. The speed of light.
Exactly. The radio frequencies that the Max Planck team analyzed, the photons that were warped into the Einstein ring in 2022, they have been traveling across the intergalactic medium for 456 million years.
Because electromagnetic radiation and gravitational waves both propagate at the same fundamental speed limit, the speed of causality in a vacuum.
So this 100-year countdown to the merger, it is based entirely on the state of the system 456 million years ago.
Yeah, it's a snapshot from the deep past.
Meaning the in-spiral, the final coalescence, the massive ring down of the newly formed hypermassive black hole. All of those violent events actually occurred during the Ordovician period here on Earth.
Hundreds of millions of years before the first dinosaurs even appeared.
The cataclysm has already happened. The colossal gravitational shock wave from their final impact has been expanding outward through the universe ever since. It has already silently torn through the dark void, washed over countless star systems and unknown worlds in the intervening space.
We aren't predicting the future at all.
No. We are simply waiting for the violent geometry of that ancient collision to finally wash over our arrays. Until next time, keep looking up.